Industrial energy waste is a direct subtraction from a facility's operating margin. A single inefficient boiler or a leaking compressed air line represents thousands of dollars in lost profit, hidden within the monthly utility bill. To reclaim these losses, you need a structured approach. Today, we are walking through a 5-step energy audit blueprint designed to locate these leaks and convert them into prioritized capital investments. Before we take a single measurement, we need a team with clearly defined roles. As shown here, a successful audit requires a team lead to coordinate with management, field engineers for site measurements, data analysts to perform energy balance calculations, and a site liaison to provide operational context. A comprehensive audit generates thousands of data points, from individual meter logs to equipment efficiency trials. This specific team structure ensures that the volume of collected data is filtered and interpreted correctly, preventing the project from stalling at the analysis stage. Step 1 is defining the audit's scope. As you can see in this roadmap, the first phase requires drawing strict physical and operational boundaries around the facilities being assessed and setting a rigid timeframe before any instruments are deployed. Looking at these panels, you must select the appropriate depth for your investigation. You might need a rapid walkthrough audit to spot obvious inefficiencies, a general audit with detailed calculations, or a comprehensive investment-grade study designed to support major project financing. The choice depends entirely on your capital objectives. If you fail to lock in exactly what deliverables are expected up front, you invite scope creep. Without a clear boundary, the engineering team and the site management are guaranteed to have misaligned expectations by the end of the project. Moving to the second phase of our sequence, Step 2 requires the team to map out the facility's production processes. We have to understand the operating schedules, load profiles, and seasonal variations to gain true operational context for the numbers we're about to record. This step also mandates a direct consultation with senior management. The audit team must establish exact economic guidelines, including acceptable payback periods and strict return on investment criteria for any future recommendations. Producing a technically brilliant engineering solution is completely useless to a facility manager if it violates management's predefined financial thresholds. The engineering must serve the economics. Step 3 brings us to the database phase, gathering the ground truth. This is a dual-track process. We combine a desktop analysis of utility bills and energy contracts with precise physical site measurements of electrical demand and process line consumption. Here, we follow the golden rule of energy auditing: never estimate a value when you can calculate it, and never calculate a value when you can physically measure it. However, auditors must avoid the trap of over-precision. Chasing extreme accuracy wastes valuable field time when simple tools are often enough to draw the correct conclusions. Sometimes a bucket and a stopwatch are all you need to accurately measure a fluid flow rate. Another major pitfall is measuring equipment exclusively during normal, steady-state production runs. This creates a massive operational blind spot. To find the real waste, you have to monitor the systems during abnormal periods. System startups and shutdowns put sudden, heavy mechanical stress on equipment, and these transitional states frequently reveal the facility's largest hidden energy losses. If you extract perfect, highly precise measurements from the wrong operational window, you will end up with mathematically flawless, but practically worthless conclusions. That brings us to Step 4, marked by the speedometer icon: assessing performance. We use our field data to construct a facility-wide energy balance, accounting for every single kilowatt-hour entering the boundary and tracking exactly where it is consumed or lost. This dashboard illustrates the primary metric for management: specific energy consumption, or SEC. This indicator normalizes the energy consumed against the actual volume of production output, like kilowatt-hours per ton of product. It is the definitive baseline for manufacturing efficiency. With our baselines established, we reach the final step in the sequence: systematically identifying energy conservation measures, or ECMs, to drive that energy consumption down. We evaluate every proposed measure through a rigorous framework. As shown in this diagram, each idea is judged strictly on its technical feasibility, its financial payback, and the implementation risk it poses to the facility. If it passes, it gets categorized. We break measures into financial tiers: Base tier includes immediate, zero-capital operational changes like switching off idle equipment. Moving up, we compare medium-cost upgrades against heavy capital investments like boiler replacements. These top-tier projects offer higher absolute savings, but must be carefully phased over time. Sorting these measures by rigid financial tiers protects the facility's immediate cash flow, while systematically guaranteeing efficiency gains year over year. All of this fieldwork culminates in the primary deliverable, the audit report. This document translates weeks of raw field measurements into a clear, prioritized executive action plan for site management. The moment this report is handed over, management should execute the Tier 1 quick wins immediately. Achieving these high-return, low-complexity measures builds team momentum and validates the accuracy of the audit's projections. This creates a robust, self-funding financial strategy. You capture the immediate cash flow generated by those initial low-cost savings and reinvest it directly to fund the medium-cost capital upgrades, which then fund the major overhauls. Following this 5-step protocol transforms the energy audit into an active financial instrument. It provides a technical roadmap that allows management to systematically improve the facility's long-term operating efficiency.